So now that we've spoken about the models and how we build these models, how we run the models, and even the weaknesses of these models, how do we use these to predict what may happen in the future and the impacts of climate change on society? So we have to go through various stages. The first stage is we have to estimate what may happen to the emissions of greenhouse gases in the future. Now for this we have to decide or have some knowledge about how population is going to change in different countries of the world, how our use of energy is going to change in the future. Are we going to move to renewable energies, or are we going to stay with the fossil fuels? Various economic models. There are many factors we have to try to understand and how they're going to change in the future, which will affect the emissions and of pollutants of greenhouse gases into the atmosphere in the future. Once these emissions get into the atmosphere, then we have to calculate what is the concentration that remains in the atmosphere. As we've learned throughout the course, when we put greenhouse gases into the atmosphere, they don't all remain there. Some of them can be taken up by photosynthesis, say carbon dioxide removed by the biosphere. The oceans also absorb some of them. So we need to know something about the carbon cycle, the chemistry in the models, to try to estimate what will remain in the atmosphere, how much carbon dioxide, methane, sulfates, and other materials will remain in the atmosphere at any time and at any location as a result of these emissions. Once we know the concentrations and how they may change as a function of time, we can then put this as the initial conditions into the global climate models. We can put them into the models, let the models again run to equilibrium, and we can couple these with the oceans, and then we can come out when we have an equilibrium of what the temperature is, the rainfall, sea level at different parts of the planet. But these are on the global scale. If we want to then go to a regional scale and see what happens just in the Mediterranean or over southern Africa, we need additional models, what we call regional climate models, which will scale down and maybe go to 1 kilometer resolution. When we go to very high resolutions, we can then resolve mountain ranges, islands, and so we have a much better detail of the regional climate, which is driven by the global climate. And then we can get some information about extreme weather, about flooding, and other issues which are important on a regional scale. And once we know that information, we can then try to understand how this will impact society, impact countries, the economy of countries, and we need additional models which will be looking at these impacts. Things like extreme weather, food security, how will the changes in the climate impact the growth, agricultural yields, etc., health issues. And so we have to go through all these different steps in order to get a scenario of how the climate is going to impact our lives in the future. And each of these different colored boxes has many uncertainties. We don't know what will be in the future with the emissions. We still have uncertainties of how those emissions get converted to concentrations in the atmosphere. Obviously, the global climate models I've spoken about are imperfect. There's a lot of uncertainties, and the resolutions are not the best that we need. The same with the regional models. They're on a much smaller scale, and the impacts also are related to how all of these parameters impact with society, with economics, with politics and policy. Well, given all of those uncertainties, we can still try to estimate what may happen in the future. And that's what's done by the IPCC reports in every report which comes out, and this from the 2021 report, which shows the possible scenarios of global temperature in the future by the end of the century, 2100. And we see that there are a number of scenarios, basically depending on what we do in the future. So the blue curve at the bottom is the most optimistic, the very low emissions. And this is if we dramatically convert our energy sources from fossil fuel to renewable energies. And we'll still see an increase in temperature for maybe another decade or two, but we may reach our maximum temperature in 2050, a little bit above 1.5 degrees above pre-industrial, and then it may start to decrease by the end of the century. If we do nothing really, if we continue as kind of business as usual, we'll have the red curve at the top, where we may actually get to about 4.5 degrees warmer than the temperatures today. But things are happening, and we are moving away from fossil fuels, maybe not fast enough. So the best estimate is we'll be somewhere in the middle, maybe between 2 to 3 degrees warming by the end of the century. I should point out that this grey banner in the middle, we've spoken about this before, which is written the Paris Agreement from the United Nations conferences in Paris in 2015 and recently in Glasgow and in Sharm el-Sheikh. The scientists put a threshold that we shouldn't pass 1.5 or maximum 2 degree global warming relative to the pre-industrial period. If we do, we may face dangerous climate change. It may be objective or subjective what dangerous means, but basically any increase of temperature, another half a degree, every half degree increase, we're going to see more natural disasters, more damage, more infrastructures impacted, more people dying. And so it's just going to get worse and worse the higher we go up with global temperatures. In addition, we may reach some tipping points or points of no return, where even if we cool the climate afterwards, we'll basically be stuck in a new type of climate. We spoke about this when we spoke about sea level rise, that once we melt the ice caps and sea level rises, it'll be very difficult to go back in time because we have to take that water out of the oceans. We first have to cool the climate and produce snow and ice sheets. And therefore, this threshold of 1.52 degrees is also related to tipping points that we may cross. And we don't really know because this is the first time we're doing such an experiment with the planet Earth. Now, if we look at different scenarios going into the future, again from the 2021 report of the IPCC, the colors here again represent those curves on the previous plot, going from the most optimistic on the left, the SSP1, going out to SSP5 on the right, which is the pathway with the most pessimistic scenario. What we see here in the left bar, in all of them, we can see the observed warming. The darker part of the bar you can see at the bottom part is what is already been observed today, and the lighter shading above it is what's expected if we follow these different scenarios to the end of the century. And next to them, we see the different contributions from, first of all, CO2. So the second bar on each of these color plots represents the contribution to global warming just from carbon dioxide. And we can see that in all of these, and especially when we go out to SSP5, the majority of the predicted warming in the future is from carbon dioxide. Next to that plot is from all the other greenhouse gases, which are not carbon dioxide, methane, N2O, ozone, chlorofluorocarbons. These also have an effect, but much smaller. Altogether, still a lot smaller than carbon dioxide. And then the fourth bar in each one of these, which is negative, is showing the cooling effects due to aerosols and changes in land use, deforestation, which are actually causing a slight offset of global warming. But what we see is the contribution to global surface temperature increases for the different emissions and will be dominated really by the carbon dioxide emissions. So this is one of the reasons that we talk often about carbon dioxide, reducing the carbon dioxide, because carbon dioxide is having the biggest impact on changes, temperatures, and global warming in the future. Another interesting thing, and we've spoken about this during the course, is that some of the carbon dioxide going into the atmosphere is again taken up by the oceans and by the biosphere through photosynthesis, absorption in the oceans. But the fraction that gets taken up is going to decrease on a relative basis as we go to the more extreme scenarios. So if we look at the most optimistic scenario in the light blue, we can see that 70% of the carbon dioxide being released today into the atmosphere is taken up by the biosphere, by the land surface, and by the oceans. 30% remains in the atmosphere, and that's what we measure in the atmosphere. But as we go to the more extreme scenarios, the SSP5, we can see that in the future, if we follow that track, only 38% will be taken up by the land surface and the oceans, and the majority of it is going to remain in the atmosphere. So the proportion of the carbon dioxide emissions taken up by the land and the ocean, the carbon sinks, what we call carbon sinks, gets smaller in the scenarios with the higher cumulative carbon dioxide emissions. So this is worrying, that as we actually warm the climate and we put more greenhouse gases into the atmosphere, we can rely less and less on the help from the biosphere and the oceans to take these gases, and especially carbon dioxide, out of the atmosphere.